We are in Chapter 2, Differentiation, Basic Concepts. Section 2.1 is the derivative. One of the main applications of calculus is determining how one variable changes in relation to another. And so what we first have is more of our algebra concept, which is called an average rate of change between 2 points, a comma f of a and b comma f of b is f of b minus f of a over b minus a. And you'll notice that this is just the slope formula. It's just written a little different rather than y2 minus y1 over x2 minus x1. And the average rate of change is the same as the slope of the line segment connecting 2 points. That is that the slope of the secant line is going to be our m equals y2 minus y1 over x2 minus x1. And again, this is the slope of a secant line, and it's also what you get by connecting 2 points with a straight line. So the example right below says find the average rate of change for the function y equals negative 4x squared minus 6 between x equals 2 and x equals 6. So if you notice, we have our x values, but we do not have those y values or those function values. And so we need to find our first value by plugging in 2, and the second one by substituting in 6. And so substituting in 2, we have negative 4 times 2 squared minus 6. And our 6 value, the second value we have is negative 4 times 6 squared minus 6. And so when substituting in 2, we get negative 22. And substituting in 6, we get negative 150. And so in order to find this average rate of change, we're going to have f of 6 minus f of 2 all over 6 minus 2. And again, just like when we worked out slope back in algebra and earlier in this class, it doesn't matter the order, just be consistent. It would also be the same if you did f of 2 minus f of 6 over 2 minus 6. And so we have f of 6 is equal to negative 150 minus f of 2, which is negative 22, all over 6 minus 2. Continuing this on, we get negative 128 all over 4, which equals negative 32. And so this would be our rate of change or an average rate of change. Right below this, we have an idea of a tangent line, which you might have seen back in geometry. To a point on a curve is a straight line that only touches the curve at a single point versus the secant line, which was discussed right up above, which was going through 2 points. Tangent line is just a single point near the point, and it just touches or grazes the curve at that one point. And so you can see the picture right next to it, that tangent line. So we have a curve and then a straight line that makes our tangent line. So the graph below shows the tangent line at point P and the secant line joining together P and Q. And so in the first graph that we have, you'll notice that your secant line and your tangent line are very different. But as point P and point Q get closer and closer together, like as you can see, as these 2 points get closer and closer and even closer together, your secant and tangent line become more similar to one another. And so with that said, it says notice how point Q moves closer to P. The distance between A and X, which is discussed down here on the x-axis, is getting smaller and smaller. And the slope of the secant line is looking more and more like the slope of the tangent line. So a derivative measures the steepness of a graph of a function at some particular point on the graph. Therefore, the derivative is the slope of the tangent line at a given point. So the derivative is the slope of the tangent line at a given point. The derivative also represents the instantaneous rate of change, and the derivative is the limit of the difference quotient. And so in algebra, we were able to find this slope or this instantaneous rate of change or the slope of a line by using 2 points or a secant line. Now we're extending this to not just finding slopes of linear equations, but to being able to estimate or to find that slope of a curve at a given point. So most things in real life don't make just nice straight lines. We're dealing with exponential, logarithmic functions that are going to be curved or changing and are not always going to be a straight line. So the usefulness of a derivative is very important for calculus, especially in the business applications. So rate of change is how fast something is growing or declining over time. And as a business owner or as somebody working with a business, this is very important to know and to analyze, and it will help understand more about what's going on with your business. So the derivative of a function f at number a, down below, says to the curve y equals f of x at point p equals c comma f of c is the line through point P whose slope is, and you'll notice that we have f prime of c right here. This is explaining that we have a derivative. And we'll see in a little bit that there's different ways to write derivatives, and this is one of them. And this little prime will tell you that that is a derivative or a first derivative. And this is going to be our definition of a derivative. This is the limit as h approaches 0 of f of c plus h minus f of c all over h, provided that that limit exists. The notation f prime of x is read f prime of x, and the function f prime of x is called the derivative of f with respect to x. So this is the derivative of f with respect to x. If x is a value in the domain of f and f prime exists, then we say f is differentiable at x, and the process that produces f prime is called differentiation. So we have an example right below that says sketch tangent lines to f of x of each of the following x values. Determine whether their slope will be positive, negative, or 0 at each x value. So tangent lines, remember, only touch the graph at one point, and that's going to be that x value that is given to us. So the first x value that we have is at -6. And so at -6, I'm just going to go down to my graph and put a dot right there, put the point on our graph when x is equal to -6. Drawing a tangent line here, remember the tangent line is just going to touch at that one point that we have. And this graph, that slope of that tangent line is negative at x equals -6. So our slope is negative. The second x value we have is when x is equal to -2. So likewise, I'm going to go down from -2 and put a point on my graph at -2 for my x value. From here, I'm going to draw a tangent line. Remember that tangent line just grazes the graph at -2 for our x value. And if you notice this time, we have a positive slope. The next x value we have is when x is equal to 2. So at 2, I'll put a point on my graph and draw my line. And you'll notice that when I do this, this tangent line is going to also have a negative slope. The next one that we have is when x is equal to 4. And x is equal to 4 down here, it's a minimum on that graph. And drawing a line is going to be horizontal there for our tangent. And remember that the slope of a horizontal line is going to be 0. So right below that, it says instantaneous rate of change is the rate of change of a particular moment, which is the slope of the tangent line to a curve at a given point. And so we have our instantaneous rate of change, or our derivative, which is f prime of x, which again is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Below this, it says the function f of c is increasing if the derivative is positive and decreasing if the derivative is negative. And so this is important to know. So positive slope would mean that we have a positive derivative. Negative slope would mean that we have a negative derivative. And then the table below that says difference quotient versus derivative. So I put down some words that you'll see throughout the course, and you can see that the first column is the difference quotient and the second column is the derivative. And the formulas are identical except for the derivative one, you are taking the limit. It's as it's approaching h equals 0. And you'll notice too that for derivatives we have tangent lines, whereas difference quotients we have secant lines. Average rate of change for difference quotient versus instantaneous rate of change. Average velocity, instantaneous velocity. And then for our economic part, it'd be average rate of change of cost, revenue, or profit versus marginal cost, marginal revenue, or marginal profit. So that marginal word is going to mean taking a derivative versus the average rate of change is going to be just our slope. So again, this would just be our algebra method, and this over here would be our calculus method. So the example right below this one says find the instantaneous rate of change for the function at the given value. And so we have f of x equals negative 4x squared minus 6 at x equals 2. So in order to find our instantaneous rate of change from our table up above, we know that that's going to be the limit as h approaches 0 of f of x plus h minus f of x all over h, and again this is equal to our derivative. From here, in order to find f of x, we already have that was given to us, but f of x plus h, if you remember back earlier in the semester, we did these kinds of problems where you have to substitute this in to our function. So the limit is h approaches 0 of, and f of x plus h, every time you see an x, you're going to put x plus h. So we have negative 4x plus h squared minus 6 minus negative 4x squared minus 6. So again, this part here, and I'll go ahead and circle it, is just our f of x value that we have. And then our denominator is just going to be h. So right now, if you were to take the limit, you'll notice that you actually get 0 over 0, which we know is indeterminate. And that means that we have to simplify this. So in order to simplify this, I'm going to multiply out the numerator, combine like terms, and see if anything reduces out. So from here, we have the limit as h approaches 0. And also take a moment to make sure that you're writing limit as h approaches 0 for every single step. We have negative 4 times, and this is going to work out to be an x squared plus 2xh plus h squared minus 6. And then distributing this negative, we're going to have plus 4x squared plus 6 all over h. From here, we have the limit as h approaches 0 of, distributing the negative 4, I'm going to have negative 4x squared minus 8xh minus 4h squared. Our 6's would reduce out, and then we have plus 4x squared all over h. From here, you can see that negative 4x, positive 4x squared would sum to 0, so those are gone. I also note that every single term left has an h in it. So from here, I can factor out a GCF in the numerator. And so we have the limit as h approaches 0 of, and I'm going to factor out negative 4h. And then we have a 2x and just an h left over. And then dividing by h. From here, you can simplify this by reducing those h's. And then we have the limit as h approaches 0 of negative 4 times 2x plus h. And h is approaching 0, so I'm going to use direct substitution there. And I have negative 4 times 2x plus 0, which reduces to just negative 8x. And so this is the equation for my derivative, and we're interested in this being at x equals 2. So at x equals 2, this means that we're going to have negative 8 times 2, which works out to being negative 16. So this function at x equals 2 has a negative slope of negative 16. The next example says the revenue in thousands of dollars from producing x units of an item is r of x equals 10x minus 0.002x squared. Part A says find the average rate of change of revenue when production is increased from 1,000 to 1,001 units. Now remember that the average rate of change was that algebra approach, just finding the slope of this. And so we have two values here. It's when x is equal to 1,000 and when x is equal to 1,001. So our slope formula is our y value at 1,001 minus our y value at 1,000 over 1,001 minus 1,000. And so we have to work out both of these values. So working out and substituting in 1,001, we get 8,005.998. And then r of 1,000, substituting 1,000 into my equation, we get 8,000 divided by just 1 as we subtract those. And so this is going to work out to being 5.998. One of the big things here is that we always need to make sure we put down units. It makes a big difference when we talk about this. And this is revenue in thousands of dollars. So this is the average rate of change. So this is going to be 5.998 thousands of dollars. So thousands of dollars. And we'll say per unit, since that was what we have. And so if you wanted to, you can also rewrite this and say this is the same as $5,998 per unit. Part B says find and interpret the instantaneous rate of change, which is our derivative, of the revenue with respect to the number of items produced when 1,000 units are produced. So we are going to find our derivative. So I'm going to go ahead and put r prime of x is equal to, and our formula is going to be the limit as h approaches 0 of, and we have r of x plus h minus r of x all over h. And so we have the limit as h approaches 0 of r of x plus h is we're going to have 10 times x plus h minus 0.002 times x plus h squared minus r of x, which is going to be 10x minus 0.002x squared all over h. So from here, we have the limit as h approaches 0 of, and a lot of algebra to go through. And so we're going to have 10x plus 10h minus, and then we have 0.002 times x squared plus 2xh plus h squared. And then distributing through my negative here, we're going to have negative 10x plus 0.002x squared all over h, which is now the limit as h approaches 0 of. And so we need to distribute. So we have our 10x's would reduce. And so we have 10h minus 0.002x squared minus 0.004xh minus 0.002h squared plus 0.002x squared all over h. And again, we can reduce out these x squared terms. From here, all of the terms have an h in them, and I'm going to go ahead and factor that h out. So we have the limit as h approaches 0. You can also factor out a number if you would like. I am just going to factor out the h. And so we have h times 10 minus 0.004x minus 0.002h. And so our h's would reduce. And then taking the limit as h approaches 0 from here, that means that this h right here would go to 0. And so we now have 10 minus 0.004x plus 0. So I won't even put that term down. And so this would be the function that we have for our instantaneous rate of change. But this is asking for when x is equal to 1,000 units, which is what we are given here. This is our x value. And so I'm going to go ahead and substitute in 1,000. And so from here we get 10 minus 4, which is equal to 6. And again, this is in thousands of dollars per unit. So $1,000 per unit. Or you could just write it as $6,000 per unit. And so you can see our answer for part A was $5,998 per unit, which again is an estimate. This is just going from one unit to the next, versus this idea of just using the one value of 1,000 units. We see that this would be actually be $6,000 per unit. So we have two different methods and two different things that we're looking for. Again, the average rate of change is dealing with our secant line and given two values of x's, whereas part B is using the calculus method and using only one value. We only had 1,000 units for our x. Right below this, we have an equation for a tangent line, which hopefully looks familiar to you. It says, assuming that f of x is differentiable at x equals c, the tangent line to a graph of y equals f of x at the point x equals c is the line through c comma f of c with slope f prime of c, with the equation given by y minus f of c, which equals f prime of c times x minus c. So for me, I don't remember this using this type of notation. I remember it from algebra, and that's our point slope formula. So y minus y1 equals m times x minus x1. So we have types of non-differentiability, which means that something that's not differentiable, which means we cannot find a derivative. And so it says a continuous function is not differentiable at cusp, vertical asymptotes, and corners. The reason why it's not differentiable at cusp and corners is because you can't define the tangent line. It kind of teeter-totters on that point, and so we can't define it. Vertical asymptotes, the slope is undefined at those. It does say underneath it, it says if f is differentiable at c, then f is continuous at c. Differentiable applies continuity. It says if f is differentiable at x equals c, then f is continuous at c. If a function is discontinuous at c, then it is non-differentiable at c. Note, continuity does not guarantee differentiability, so it doesn't work the other way. So definitely things to keep in mind.